Hello friends, welcome to CareerClust Learning. Today we are going to discuss about a quick revision of top 15 system design concepts. System design is very important subject to clear an interview. These days the interview process is a bit tough one. It is very important to have very clear knowledge of system design concepts. If you are new to our channel, please like, share and subscribe. This will encourage us to make more number of videos. Thank you. In system design, the first concept is scalability. A system's ability to handle growing amount of work by adding resources. It means if the more number of work is assigned to a system, and the system should be able to handle that work and it will complete without any interruptions or without any issues. A simple explanation: scalability means your system can serve 10 users or 10 million users without breaking. It involves designing architecture that grows gracefully as demand increases, either by upgrading machines or adding more of them. Okay, we can discuss this further. Think of it as like a highway system. You can widen existing lanes, existing roads, that is a vertical, or build a new parallel roads, that is horizontal, to handle the more traffic. This analogy will keep you to understand more about this scaling, vertical scaling and horizontal scaling. So we can discuss this vertical scaling and horizontal scaling in detail in the further topics. Why it matters? The foundation of system design, very large scale system, must be built with scalability in mind. It means, so if the traffic in the application is increases, the system should be in a position to handle that work without any breaking. Common uses are handling user growth, managing traffic spikes, processing increasing data volumes, supporting global expansion. Some real world examples are Instagram scaling from 0 to 1 million users, 1 billion users. Twitter handles spike during the major events. Shopify managing Black Friday traffic surges. So to handle these kind of traffics, system should be in a position to handle this. Coming to vertical scaling and horizontal scaling. A vertical scaling is increasing the system capabilities like increasing RAM, memory and processing speeds, etc. And horizontal scaling means, as already mentioned in the analogy, build new parallel roads. Means we can increase more number of machines, more number of similar machines to handle that load. This is about scalability. The next concept is load balancing. Load balancing is very important concept in system design. What is load balancing? Distributing income requests across multiple servers to prevent overload. It means distributing the work to multiple servers in the same network. Simple explanation: load balancers sit between users and servers, routing each request to the least busy server. They are algorithms like round robin, least connections, or weighted distribution to spread traffic evenly. It means if a server is having 4 to 5 different machines, 4 to 5 different servers, then the load balancer will take the responsibility to distribute these incoming requests according to the priority or according to the algorithms designed. So to make the processing reliable without breaking it, or that will not make any server overburdened with the request. Think of it as like a bank with multiple tellers. A greeter directs each customer to the next available window, so no one waits too long. I hope you understand this. Why it matters? essential for high availability and ensuring no single server becomes a bottleneck. Some common uses of load balancing are traffic distribution, health checking, SSL termination, session affinity, and failover handling. Some real world examples are AWS ALB routing API request, Nginx distributing traffic to backend servers, DNS based global load balancing. This is about load balancers. The next concept is caching. Caching is also a very important term in the system design. Let's see what is caching. Storing frequently accessed data in fast storage to reduce load and latency. Caching keeps copies of expensive to compute or frequently requested data in memory for instant access. It dramatically reduces database load and response times but requires strategies for keeping cached data fresh. So it means instead of making a request to database, so we keep the data in a very frequently accessed data in the memory, and whenever the user makes a request, the system checks in the cache and that will serve without making a database call. Think of it as like keeping your most used tools on your desk instead of walking to the storage room every time. Faster access to things you need often. I hope you understand this. Why it matters? The single most effective technique for improving system performance and reducing cost. Some common uses: reducing database queries, speeding up page loads, storing session data, API response caching, computed result storage. Some real world examples are Redis caching user sessions, CDN caching static assets globally, browser caching CSS and JavaScript files. This is about caching. Let's go to the next term, that is database sharding. What is database sharding? Splitting a database into smaller pieces distributed across multiple servers. Simple explanation: sharding divides your data horizontally. For example, users A to M on one server and N to Z on another server. Each shard holds a subset of the data, allowing the system to handle more data and queries than a single server cloud. It means instead of maintaining a single database that will give performance issues, and we divide that entire database into different parts and storing them in different servers based on location or based on usernames or based on anything. Think of it as like splitting a phone book into volumes by letter. Each volume is smaller and faster to search through. Why it matters? Enables databases to scale beyond the limits of a single machine. Some common uses of database sharding: horizontal data partitioning, distributing write load, reducing query scope, and geographic data locality. Some real world examples are Instagram sharding user data by user ID, MongoDB auto sharding collections, and Vitesse sharding MS SQL for YouTube. So, for example, if a user is making any request to Instagram from India, so the database sharding, if it is have India-based sharding, and it will be available in Indian data centers, and the request time, the round trip time will be very quick to get the data. This is about database sharding. The next important thing is cap theorem. This is one of the important concepts in system designs. A distributed system can only guarantee 2 of 3 They are CAP: consistency, availability, and partition tolerance. It means we cannot achieve these three required things at a time. So if you want other two, we need to compromise on one. Simple explanation. CAP theorem states that during a network partition, you must choose between consistency, all nodes see the same data, and availability, every request gets a response. You can't have both of them when the network fails. So you can have any one of it. Consistency and availability together, or availability and partition together, or consistency and partition together, but not three at a time. Like a group project, during a communication breakdown, you either wait until everyone agrees, that is consistency, or let people work independently, that is availability, but not both. Why it matters? A fundamental trade-off that guides every distributed database design decisions. Some common uses: some database selection, system architecture decisions, trade-off analysis, distributed system design. Some real-world examples are MongoDB choosing CP, consistency over availability; Cassandra choosing AP, availability over consistency. It means availability and partitioning. CP means consistency and partitioning. Traditional SQL databases choosing CA. So it's here no partitioning required, but consistency and availability. So this is all about CAP theorem. CAP means consistency, availability, and partition tolerance. The next term is microservices. So this is very important one in current computer systems or current software development. Microservices. What is microservices? What is microservice? Architecture pattern where an application is composed of small and independent services. It means an application is composed of small and independent services. So instead of having one application which handles everything, so this can be identified on the independent services and designed in a way that it is independent from other service, and it is a smallest application to perform the task. Simple explanation. Microservices decompose a monolithic application into loosely coupled services that communicate via APIs. Each service owns its data, can be deployed independently, and can use different technologies. So we have a concept of monolithic applications, microservices applications, and monorepo applications as well. So if you think of monolithic applications, a monolithic application is an application which is having everything in one application, that is having a common database, and it is common for all the services in a project. But a monolith for performance and easy maintenance kind of things, a monolithic application can be divided into multiple independent parts with a loose coupling, and each can serve the people with its own data, and they can communicate with APIs. Think of it as like a shopping mall versus a departmental store. Each shop, that is service, operates independently with its own stuff, inventory, and hours. Why it matters? Enables large organizations to build and scale complex systems with autonomous streams. Some common uses are independent deployment, technology diversity, fault isolation, team autonomy, and selective scaling. So the one more power of this microservices is one service can have a different technology like Java, another can have another technology like Python, and another application, another microservice can have again a different technology like .NET. But in turn, these three applications can communicate with APIs. Some real world examples are Amazon's hundreds of services behind their website. So if you see Amazon website, it is being running with multiple microservices. Uber separating rides, payments, and maps. So Uber also provides microservices, a service different from rides and different for payments and different for maps. Netflix 700 plus microservices. So all this is about microservices. The next very important term is API gateway. What is API gateway? API means application programming interface. What is API gateway? A single entry point that routes client requests to appropriate backend services. Simple explanation. An API gateway sits between client and microservices, handling, routing, authentication, rate limiting, and response aggregation. It simplifies the client experience by providing one unified interface. We can handle these concepts like authentication, rate limiting in other topics. Think of it as like a hotel concierge. Guests make one request and the concierge coordinate with housekeeping, restaurant, and transport behind the scenes. Why it matters? Simplifies client service communication and centralizes across cutting concerns. Some common uses: request routing, authentication and authorization, rate limiting, response aggregation, and protocol translation. Some real world examples are Kong managing API traffic, that is Kong gateway, AWS API gateways for serverless backends, Netflix Joule routing millions of requests. This is all about API gateway. It is kind of a gate and that will handle all the requests in reaching the backend service. And another important point is message queue, a system that enables asynchronous communication between services via messages. Some simple explanation is message queues decouple services by letting them communicate through a buffer. The sender puts a message in the queue and moves on. The receiver processes it when ready. This handles traffic bursts and prevents cascading failures. This is message queues. The sender sends the request and that stores in a buffer, and whenever the receiver accepts it and he processes it and sends the data. That is message queue. An example, think of it as like a mailbox. You drop off letter and go about your day. The recipient picks it up and reads it when they are ready. So there is no need of waiting for the response. Why it matters? Critical for building resilient decoupled systems that handle variable loads gracefully. Some common uses are asynchronous processing, load leveling, service decoupling, event broadcasting, and task scheduling. Some real world examples are RabbitMQ handling order processing, Apache Kafka streaming real time events, AWS SQS managing backgroup job queues. This is all about message queues. And the next term or ninth term in our series is rate limiting. What is rate limiting? Rate limiting is controlling how many requests a client can make within a time window. Simple explanation. Rate limiting protects your system from being overwhelmed by too many requests. It sets boundaries like 100 requests per minute per user and rejects the queue's excess request. It means, so if a server is getting a lot of requests from a single user, it will not have time to serve other users. So that is the reason they put some rate limiting, and they put a condition like in a second or in a minute they can accept some n number of requests, and for other exceeding requests they need to wait for some other time slot. Think of it as like a bouncer at a club with a capacity limit. Once it's full, new people have to wait, regardless of who they are. Why it matters? Protects system from abuse, DDoS attacks, and ensures fair resources usage. Some common uses of rate limiting: API protection, DDoS mitigation, fair usage enforcement, cost control, and service stability. What is DDoS here? DDoS is distributed denial of service. It means making a million number of requests in a single second to a system to make the system down. This is an activity usually hackers do. Some real world examples are Twitter limiting API calls to 300 for 15 minutes, GitHub rate limiting unauthenticated request, Stripe routing payment API calls. All this is about rate limiting. Our next concept, consistent hashing. This is 10th term in our system design concept. What is consistent hashing? A technique for distributing data across nodes with a minimal redistribution when nodes changes. Simply, consistent hashing maps both data and servers onto a virtual ring. When a server is added or removed, only a small fraction of data needs to move, unlike traditional hashing where everything reshuffles. So it means this consistent hashing makes an algorithm that handles whenever there is any change in a server list or nodes, there will be a minimal amount of data to migrate to one machine to another machine. Think of it as like assigned seats in a circular theater. When a new section opens, only nearby people need to move, not the entire audience. I hope you understand this example. Why it matters? Enables efficient scaling of distributed caches and databases with minimal disruptions. Some common uses are distributed caching, load distribution, database partitioning, CDN routing, and peer-to-peer networks. Some real-world examples are Amazon DynamoDB distributing data across nodes, Memcached cluster scaling, and Cassandra's data distribution ring. So another very important term is replication. What is replication? Replication means maintaining copies of data across multiple servers for reliability and performance. So it means making a copy of available data into other 2 or 3 different copies and store that in a different location. In case of any failures or any data loss, then the data should be available in a different copy to serve the purpose. Otherwise, that will go into a problem. Simply, replication keeps identical copies of your data on multiple machines. If one server fails, others have the data. It also allows read traffic to be distributed across replicas for better performance. Think of it as like making photocopies of important documents and storing them in different locations. If one of it lost, you have backups. Why it matters? The primary mechanism for achieving data durability and high availability. Like replication is like if you have a original certificate, you can have multiple Xerox to it. So you can give the Xerox as alternative to original. Why it matters? The primary mechanism for achieving data durability and high availability. Some common uses are high availability, disaster recovery, read scaling. geographic distribution, and data durability. Real world examples are MySQL master slave replication, MongoDB replica sets with automatic failover, PostgreSQL streaming replications. Next is another very important is horizontal versus vertical scaling. So in the first term we learned about what is scaling. Scaling means the system should be in a position to handle uneven increase of the request. So it should be handle 10 requests, or it should be in a position to handle 10 million requests at a time. So what is horizontal scaling and vertical scaling? Adding more machines means horizontal, versus upgrading existing machine is vertical. This is a simple definition. In simple words, vertical scaling means getting a bigger, more powerful server. Horizontal scaling means adding more servers to share the load. Most large systems use horizontal scaling because there is a limit to how big one machine can get. So we cannot increase resources to a single machine in very large extent. That is the reason in many systems go with the horizontal scaling. Think of it as vertical is like replacing your car with a bus to carry more people. Horizontal is like adding more cars to carpool, both move more people but efficiently. Why it matters? Understanding these trade-offs is fundamental to designing systems that grows efficiently or effectively. Some common uses are capacity planning, cost optimization, architecture decisions, and performance improvements. Some real world examples are adding more web servers behind a load balancer, that is horizontal, upgrading database, RAM, and CPU, that is vertical, and Kubernetes adding pods for horizontal scaling. So these are few examples. This is all about horizontal scaling and vertical scaling. The next concept is CDN, Content Delivery Network, a global distributed network that serves content from nearest edge location. CDN places copies of your content on servers worldwide. When a user in Tokyo requests your website, they get it from a nearby server instead of your origin server in New York, dramatically reducing latency. So it means the CDN, Content Delivery Network, makes a distribution of your data, and whenever a user makes a request from a location, and the nearest data center or nearest server will serve that request, and that will increase the performance and that will reduce the latency. Think of it as like a franchise restaurant chain. Instead of everyone traveling to the original location, there is one nearby that serves the same food. So as we have some multiple chain of paradise biryani centers in all over world, so we can request any nearby franchise to get it. This is about CDN. And why it matters? It is essential for delivering fast experiences to users regardless of their geographic locations. Some common uses are static asset delivery, video streaming, API acceleration, DDoS protection, and edge computing. Some real world examples are Cloudflare protecting and accelerating websites, AWS CloudFront serving Netflix content, Akamai delivering 30% of global web traffic. These are few examples of CDN, Content Delivery Network. This is about CDN. The next one is circuit breaker. Circuit breaker. What is circuit breaker? A pattern that prevents cascading failures by stopping calls to failure services. Like an electrical circuit breaker, this pattern monitors for failures. When a service fails repeatedly, this circuit opens and immediately returns errors instead of waiting for timeouts, giving the failing servers time to recover. So for example, if a service is not responding for first 5 requests, then this circuit breaker will stop sending the request to it, and it give the time to make that service up and running. Like a fuse in your house, when there is an electric overload, it strips to protect the whole house from catching fire. I hope you understand it. So if the fuse is not placed in correct location, so if there is anything happens with the power in house, so that will catch fire in the house, but the fuse will put off the fuse will cut down the power supply to other locations when there is anything happens behind. Why it matters? Prevents one failing service from bringing down the entire system. It means if a system is having 5 different servers and one server is getting failed, so it makes one server is not available from the entire system, but it will not fail all the entire system. Some common uses are failure isolation, graceful degradation, fast failure response, service recovery time, and cascading failure prevention. Some real world examples are Netflix high-stakes protection against service failures, resilience 4J in Spring Boot applications, and NY proxy circuit breaking in service meshes. This is all about circuit breaker. The final word for today's discussion is event-driven architecture. What is event-driven architecture? EDA. A design patterns where services communicate through events rather than direct calls. Simply, in event-driven architecture, services emit events when something happens, and other services react to those events, which creates loose coupling. The sender doesn't need to know who is listening or what they will do. Like a newspaper, the publisher prints news, that is events, and the subscribers read what interests them without the publisher's knowledge who they are. Why it matters? Enables highly scalable, loosely coupled systems that can evolve independently. Some common uses real-time processing, service decoupling, event sourcing, CQRS pattern, and reactive systems. Some real-world examples are Uber processing ride events in real time, e-commerce order events triggered inventory, shipping, and email services, IoT, Internet of Things, sensor data streaming through event pipelines. This is all about event-driven architecture. That's all about today's discussion and top 15 system design concepts. This is very useful for your interview purpose. Thank you everyone for watching. Please like, share, and subscribe. Share your thoughts in the comment section. I will make more this kind of videos in the future. Thank you.